Alright, welcome back to another physics lesson. Today we're doing chapter 8, specifically lesson 2, or on your worksheet it says lesson 11 for this unit, on magnetic force on moving charges. Now this is going to be my last lesson for this week because I'm getting a lot of questions on the labs and I don't want to leave anybody behind. So take this week and the weekend if you need it to catch up, getting your homework questions done, making sure you understand what we've done so far in electricity and magnetism. Okay, also this lesson is a big one as I will be going over J.J. Thomson's discovery of the electron and how that led to the mass spectrometer. Alright, let's get started then. So if we have a charged particle moving through a magnetic field, I'll just get it. Here, this will work. Alright, we have a charged particle. It's actually just a moon filter for a telescope, but let's pretend. We have a charged particle moving through a magnetic field. So let's say there's a magnetic field everywhere going into your screen. Okay? It's going to feel a force acting on it. Why? Well, you can think of it like this way. If you have a moving charged particle, it's going to create its own magnetic field, and that magnetic field is going to interact with the magnetic field it's moving through. Now, the equation that describes this is a cross product between the velocity of the particle and the magnetic field it's going through. And of course, you need to multiply that by the charge. That's another important factor. Right? So how we're going to solve the cross product is just write it as Fm equals QVB sine theta, where theta is the angle between V and B. Now in almost all the questions I'm going to give you, V is going to be perpendicular to B. I mean, that's the most efficient way if you're trying to get the greatest force acting on a charged particle, you make that magnetic field perpendicular to the velocity of the particle. That way, you get theta equals 90 and sine of 90 is 1, the biggest it can be. Okay. That being said, the direction is with the right hand rule. Now this picture shows a hand, but where are we here? I like doing this because I can actually see a finger pointing in every direction. So if we follow this, your thumb, okay, on this picture it says I, current, but that can also be the same as V, right? The velocity of your charged particles. Okay, and remember we're doing conventional current, so you can imagine this as being the velocity of a positively charged particle, right? Here's the direction of the magnetic field, B, and the direction of the force is here, all right? Notice that all three vectors are perpendicular to each other. Or, well, mainly the most important thing is that our third vector here is perpendicular to both our first two vectors. Alright, so I said this is for a positively charged particle. Well, what if it's a negatively charged particle? Use your left hand. This would be your left hand rule. If you have a negatively charged particle, use your left hand. Okay, very important. Right hand positively charged particle, left hand negatively charged particle. Okay, you probably won't be writing a test, but usually what I find is this is difficult for people who are right-handed because they tend to be stressed on a test and they hold their pencil in their right hand and they don't want to drop their pencil, so they get a question and they immediately put out their left hand, even if it's for a positive particle. It's like, no. Okay, so you need to relax, take out both hands. Which is it? Right positive, left negative. Okay. And there are some cool examples. This is called the magnetic hydrodynamic propulsion ferry. Okay, and what happens is this only works in seawater. Right, so this is in seawater, and underneath this boat here, underneath this ferry, we have these two parallel plates. Okay, one positive charge, one negative charge, and because we're in salt water, right, we can get a current going across the water. Okay, and you can see the direction of the current is, again, conventional current. All right, and then we also have a strong magnetic field produced by the boat, in this case, upwards. And so if you were to do your right hand rule, Right? For conventional current, it's right hand. If you ever decide you want to do electron flow, left hand. Okay, because conventional current, we have the positive charges moving. Okay, so try this. I think it might look backwards with the video. So try it yourself. Put your thumb in the direction of the current. Put your index finger in the direction of the magnetic field, and your middle finger will point in the direction of the force. So what's happening is there's a force being exerted on that seawater pushed out the back of the boat. Newton's third law says you push that out the back, it's going to push you or the boat forward. And so it's a really cool propulsion system. Okay, now let's imagine let's take this charged particle, we'll make it positively charged, and we'll have it go across in this direction, going straight. Now there's a magnetic field going into the screen, or from your point of view, I'm probably pointing out of the screen. This is going to get a little confusing. Can't even point properly. There we go. Okay, so it's moving in this direction, and the magnetic field is in this direction. What direction will it feel a force on? Well, take your right hand, because I said it's a positively charged particle. Our thumb's going to go in the direction that it's moving in. My index finger will go in the direction of the magnetic field, and the thumb goes in the direction of the force. So it's moving this way, but it's feeling a force up, so it moves up. As it moves up, you have to curve your hand with it, because your thumb curves with the velocity. And so what happens is the force keeps changing. Right? And notice now that magnetic force really is a centripetal force, as it's always pointing towards some center-seeking area. And your particle starts moving under centripetal motion. Yes, we're going back to this. We should be good with this. I taught this in class before we did this online thing. Okay, so basically, the magnetic force is a centripetal force, or can be a centripetal force. And you can do the same thing with a negative particle. If I made this negative, it would just go the other way. All right, so there's another example. Take a look at that picture. Okay, here we have a negative particle. So choose any one of the V vectors, any one of the red arrows, and put your left thumb in the direction of that arrow. And then we have X's all over the screen there. Those X's are telling you that the magnetic field is going into your screen. Okay, so put your index finger going in. Right? And what direction is your middle finger? It should be going towards the center. And as you rotate your hand around that circle, your middle finger is always going to the center of the circle. All right, charge to mass ratio. So this was the experiment that J.J. Thomson did. Let me just go over this. Okay, here we have a cathode. Here we have two vertical parallel plates. So this is going to release charged particles, and we know now it's going to be electrons that are being released, but you didn't know that at the time. But we had charged particles, so we use these parallel plates to accelerate the charged particles across a potential difference. And then there's a little hole in this plate. There's a little hole, so the charged particles are able to pass through. And then here we have coils. Now these coils, you have a current going through them. Because we have a current going through them, they're going to produce a magnetic field. In what direction? You have to remember this right-hand rule. So take your right hand, because this is conventional current, and curl it in the direction that the current's going. And then your finger will point into the screen. So your finger is going to point into the screen. That's the direction of the magnetic field. Now we have these electrons moving across, right? And we can either apply a magnetic field going into the screen, or notice right here, there's two horizontal parallel plates. So we could apply a potential difference, right? Where we have a vertical electric field. So let's see what we actually did. First thing was, I went too far here. Nope, I didn't. Okay, so first thing is we turn on those coils. right? And we apply a magnetic field. When you apply a magnetic field, now let's try this with, this is actually going to be an electron. So let's use our left-hand rule, right? And we're going to put our thumb in the direction of the electron. I think it looks backwards on the video, but you do it. Okay, your thumb's going to the right, right? And then your magnetic field B is going into the screen. And then you should have your middle finger pointing down. So this is going to cause, if you turn on just the coils, it's going to cause these stream of particles to be deflected downwards towards X. And we can calculate that. We can set magnetic field equal to centripetal force. Magnetic field is QVB sine theta, but this is at 90 degrees, so sine theta is 1, and Q is for an electron, so we're just going to write E for the elementary charge, equals centripetal force mv squared over r. And we're just rearranging for what we call the charge to mass ratio. Next step is to turn on the electric field, but we're going to change the electric field. So the electric field by itself would cause the particle to be deflected upwards if we set the field to be in that direction. Well, the field wouldn't be upwards, the field would be downwards, and the electrons would then move upwards or feel an upwards force in that field and will be deflected upwards. Okay, but if we then also turn on the magnetic field and alter our potential difference so that the beam goes perfectly straight, when it goes perfectly straight, we know that the downwards magnetic force is equal to the upwards electric force. And we can set Fm equal to Fe. And therefore, EVB, again, sine of 90 is 1, equals Q epsilon, right? Charge, the elementary charge E, times the electric field strength. Now we're going to rearrange this and solve for the velocity. Notice that the charge just cancels. Now taking this velocity and this charge to mass ratio previously, we can put those two equations together to get this charge to mass ratio, which is the electric field over the magnetic field squared times by, what's that R? It's the curvature that the path took when it was under the magnetic field, the radius of curvature. Okay, and he did this experiment and he determined that the charge to mass ratio is 1.76 times 10 to the 11 coulombs per kilogram. But he's using Millikan's data. So he's using Millikan's data for the elementary charge. And when he puts that elementary charge into this equation, he gets the mass for these particles to be 9.11 times 10 to the minus 31, which is way lighter than the mass of the hydrogen atom, which was the smallest thing they knew at the time. And so this was the discovery of the electron. This discovery of the electron led to another important discovery. Oh, not as discovery, but invention, the mass spectrometer. Now the mass spectrometer doesn't work exactly like the cathode ray tube. It's slightly different. Let me just skip. We'll do these questions on the whiteboard once we get to the end. Okay, this is the last question. I'll get back to it, but let me just explain how the mass spectrometer works. The mass spectrometer is going to accelerate things through a parallel plate, and then it will deflect the objects through a magnetic field. And that's it. There's no second electric field that tries to balance that magnetic field. Instead, we just look at how much those particles going through the mass spectrometer get curved by that magnetic field. And if we know the charge of that object, how much they get curved of, honestly, depends on their mass or their inertia. Right? The more inertia they have, the more force would be required to actually curve their path. Right? And so we could actually calculate that inertia or their mass. Okay, but we're going to get there step by step. Let's go through these problems using what we've learned. All right, so on the back of the sheet, we have 4 problems we're going to go through. Let's start with the first one. First one says, what is the magnitude and direction of a magnetic field if an electron moving through it at 2 times 10 to the 6 meters per second experiences a maximum magnetic force of 5.1 times 10 to the minus 14 newtons? Sounds like a lot, but remember, we are moving an electron. Okay? When moving vertically straight up. So our equation, Fm equals QB QVB times the sine of theta. Okay, now theta is 90 degrees, so sine of 90 is just 1. And what we're trying to solve for here is the magnetic field strength. So rearranging for B, we get Fm over QV. I should write that as a small v. Be very, very clear that it's a small v, because you can see now we're using potential difference and velocity a lot in the same equation. So let's be very careful that that's a small v. Okay, and then we're just going to sub in our values. 5.1 times 10 to the minus 14 newtons over the charge of an electron, 1.602 times 10 to the minus 19, times by its velocity, 2 times 10 to the 6 meters per second. When we do that, we get 0.16. For the units, I haven't told you exactly what these mean yet, but for now, Teslas. Now we need a direction. We have it saying that the particle is moving straight up and feels a force to the left. Okay, well, right-hand rule. Or is it left-hand rule? Okay, be careful. Which is it? Is it a proton, electron, positively charged, negatively charged? This one, it says it's an electron, so we're going to use our left hand. Okay, so the velocity is with our thumb. Okay, the force is with this finger. There we go. So try it, make sure you can do this yourself, but you can see the magnetic field coming out of the board. If you don't get it coming out of the board, if you get it going into the board, you probably used your right hand. Okay, because if you use your right hand, you will get the opposite result. Okay, so this is coming out of the board. If you remember the symbol for coming out, the circle, the dot. All right, so there's our direction. Okay, all right. Question 2. Question 2 says, calculate the radius of the path taken by an alpha particle. If you remember, an alpha particle really just is a helium nuclei, so it's just a particle with 2 protons and 2 neutrons. That there is telling you the charge. I sort of give you the hint in brackets that the charge is 3.2 times 10 to the minus 19, but you should be able to figure it out. A helium or an alpha particle is a helium nuclei, and the net charge there is plus 2, so it's 2 times your elementary charge. And then the mass, you don't need to memorize the mass, is 6.7 times 10 to the minus 7 kilograms. It's injected at a speed of 1.5 times 10 to the 7 meters per second into a uniform magnetic field of 2.4 teslas. And then I add at right angles to the field. That just tells you theta is 90, sine of 90 is 1. In this case, if we inject a particle into a magnetic field, okay, it's going to undergo centripetal motion. So we can set the magnetic force equal to the centripetal force, because this is the only force that here is contributing to centripetal force. We're not going to count gravity or anything. That gravity is nothing compared to magnetic force. All right. So this is QVB times sine of theta, but in this case sine of theta is just 1, equals mv squared over r. Those v's are the same, so we can cancel one of them, and we can rearrange for r, where r equals mv over qb. Okay. Now we just sub in everything that we have. Okay, I'll let you sub in all the numbers, but we're going to end up with 0.13 meters. Okay, and that's the radius of curvature. As it enters the field and it curves, right, that would be r, 0.13 meters. Okay? Question 3. This one has 2 parts, so 3A. And I do sort of lead you into how we will solve question 4, which is the mass spectrometer. That's why I'm doing question 1, 2, and then 3 is really question 1 and 2, and then we'll put it all together. Here we have a single ionized ion. What does that mean? A single ionized. It means it has a net charge of 1. Plus 1, minus 1, I don't know, but 1. So we know the charge is 1.602 times 10 to the minus 19 coulombs. And it gives us the mass, and then it says it's accelerated through a potential difference of 1 times 10 to the 5 volts. So what is the velocity once it leaves this potential difference? This is what we did in chapter 7, right? The work done to accelerate it equals its change in kinetic energy, and assuming its initial is 0, that's just 1/2 mv prime squared. Rearranging for v prime, we get the square root of 2q delta v over m, or the square root of 1.602 10 to the minus 19 times the potential difference, which is 1 times 10 to the 5 volts, over the mass, which is 3.9 times 10 to the minus 25 kilograms. And we get a speed of 2.9 times 10 to the 5 meters per second. Okay, that's part A. Part B says, now if it's shot through a magnetic field, what's the radius of the path it would take if injected at 90 degrees, sine theta is 1, into a 0.1 Tesla uniform magnetic field. So this particle gets shot into a magnetic field, and therefore will undergo centripetal motion. So we're going to set magnetic field equal to centripetal motion. Okay, these two relationships we use a lot, right? This accelerating through parallel plates, QV equals 1/2 mv squared, and then sending it through a magnetic field where Fm equals Fc. Okay, 2 combinations we use the most in this whole unit. All right, and we are solving for R, so we lose 1v. Rearranging for R, this is just like the previous question, is mv over qv. Now we know what v is. We got that from part A. Right? And we know m, q, and b, so R is going to be 7.1 meters. And there's part B. Okay, if everyone's okay with all that, we'll go to the big question, number 4, the mass spectrometer. Okay, now remember, a mass spectrometer is not the same as a cathode ray tube. So we start by having parallel plates, put a little hole in one of them, take a charged particle, any charged particle, you can just put any sort of atoms in there and then apply an electric field to rip apart all their electrons. And so we just have the nuclei of these atoms, and so they're all positively charged. Okay? And therefore, because they're charged, they can be accelerated through a potential difference. So they get accelerated through a potential difference. Okay? And then they go through some sort of magnetic field. Okay, I just randomly chose a field coming out of the board. You can make it going into the board. But when this happens, we have our positive particle going through a magnetic field. It is going to have its path curve down. Right? Here it will be going straight because it's left of field, but we can calculate that curvature, or we can measure that curvature. We can calculate the velocity, and we have a screen over here that shows it appear right there. So that's a mass spectrometer. Different from a cathode ray tube, which also applied a potential difference with horizontal plates here and here to equalize the forces to get it to go straight. Alright, so there's no second set of parallel plates in a mass spectrometer. So that charge to mass ratio, I only derived that to show you how J.J. Thomson discovered the electron. Okay, I find a lot of people use the charge to mass ratio to solve the mass spectrometer, and that would be wrong, because that charge to mass ratio was derived for a cathode ray tube, not a mass spectrometer. Alright, so let's look at what they give us in this question. We want to find the mass of oxygen-16 with a charge magnitude of 2e. Alright, so the charge is twice the elementary charge. There's a potential difference here that accelerates it. The potential difference is 325 volts into a uniform magnetic field here, B, which is 2 teslas. And then it undergoes a curved path of radius, 0.862 centimeters. So let's change that to 0.00862 meters. Okay, so that's what we know. Now, if we were to start here, we can say Q delta V, the work done, equals a half mv squared. Now you might think, oh, there, I can solve for m. But you can't because we don't know v. You can't find v because we don't know m. But let's solve for v anyways. V equals the square root of 2q delta v over m. Okay, let's call that equation 1. Just going to erase our diagram here, so I have some room. Now once it undergoes, I erased it, but once it goes through the magnetic field, it's going to undergo a curved path because it's going to have a magnetic force causing our centripetal force. Alright, so that is QVB sine theta, but it's being put in at right angles, so sine theta is 1, equals mv squared over r. Now 1v cancels. Rearranging, we're left with QBr equals m times v. But what I'm going to do is I'm going to substitute this v up here. So I'm going to write all times by the square root of 2q delta v, right? That's potential difference, not velocity, over mass. Okay, just going to erase this now so I have some room. So now I have one equation with one unknown, m. I got 2 of them there. But before we start doing some rearranging, let's get rid of the square root by just squaring both sides of the equation. So if I do that, I'll get q squared b squared r squared equals m squared. And then we can just put brackets and drop the square root. 2q delta v over m. Now this looks much better. Okay, we're going to have that m go away. So we only have one m. It makes it easier to solve for. We also lose a q. Okay, so rearranging for m now, we get the mass of our oxygen-16 equals q b squared r squared over 2 delta v. And if you plug in q, which is 2e, e being our elementary charge that Millikan came up with, 1.602 times 10 to the minus 19 coulombs. We have b, 2 Tesla squared. We have r in meters, square that, all divided by twice the potential difference. And you get a mass to be 1.46 times 10 to the minus 25 kilograms there. We just determined the mass of those particles that we sent through the mass spectrometer. So now you know how that works and you can make your own calculations. So that's it for this video. If you have any questions, good luck. Continue to work and catch up. I won't post a new video till Monday, but don't worry, we are on track. We will get through the course. I'll be sure to see that. All right. Have a good weekend.